Hello everyone, welcome back to the video lecture series of Basic Electrical and Electronics Engineering. In this session, we are going to discuss what is magnetic field density, magnetic field strength and the relation between them. So let's get started. The magnetic flux density, which is also called as magnetic field density. Density means what? Density of any quantity will be the value of quantity divided by per unit area. So here we want to calculate the magnetic flux density. So it will be the magnetic flux per unit area. And here the area is measured in a plane perpendicular to the flux is known as magnetic flux density. It is denoted by capital B and measured in Tesla. So magnetic flux density will be the ratio of flux upon area, where flux is the magnetic lines of force measured in Webers and A is the area, so it will be measured in meter square. So the unit of B will be Weber per meter square, which is also known as Tesla. Suppose we have this magnet and this is the magnetic field of this particular magnet. These are the magnetic lines of force. Okay, this how many number of flux lines in per unit area we have, that quantity is known as magnetic flux density. And from this equation we can write phi is equal to B into A, that is magnetic flux. Phi is equal to product of B, that is magnetic flux, magnetic field density, into A, the area perpendicular to the magnetic field B. This is the magnetic flux density. In this way we can calculate the magnetic flux density of a particular magnet. Then the next term is magnetic field strength. Magnetic field strength. It is the force experienced by unit north pole placed at that point in a magnetic field. Suppose, see this figure. Suppose we have this magnet with us and this is the magnetic lines of force and this total is the magnetic field of this magnet, and we want to calculate this magnetic field strength of this particular magnet. Then how it can be calculated? It can be calculated with the help of another magnetic field. Suppose this is the magnetic field of this magnet and we have placed another magnet here. Suppose we have placed another magnet here, and this is the north pole of the second magnet. Then the force experienced by this unit north pole placed at this particular point is known as magnetic field strength H of this magnet. The force experienced by the second unit north pole, which is placed in the magnetic field of this first magnet, and it is the strength of this magnet. To calculate the strength of this magnet, another north pole is placed here, and the force experienced by this north pole gives the value of magnetic field strength. We have the expression for this magnetic field strength, and it is denoted by H. H is equal to number of turns into current divided by length. Number of turns into current divided by length. Number of turns measured, it is a quantity, so it will be number of turns T, current measured in ampere and length measured in meter. So the unit of H will be ampere turn per meter. So always the H measured in ampere turns per meter. In this way the magnetic field strength of a magnet is calculated with the help of second magnet. Then we have a relation between this magnetic flux density B and magnetic field strength H. B is equal to mu into H, where B is the magnetic flux density or magnetic field density, H is the magnetic field strength. Then this mu will be the permeability of material. It depends, the value of mu depends upon the permeability of material. Let's see what is this permeability. The permeability is the ability of material to carry the flux lines. It is the ability of material to carry the flux lines. That means it depends upon the material which we are using to carry the flux lines. Suppose the materials are such iron and steel, then they have the high permeability. If the materials such as wood have the low permeability, that means depending upon the material we are using, we have different permeability values, and it is denoted by this mu and measured in Henry per meter. Let's see this in detail. There are two types of permeability. One is absolute permeability, another one is relative permeability. It is denoted by mu and it is denoted by mu r. Let's see one by one. First one is absolute permeability mu. It is the ratio of magnetic flux density B and magnetic field strength H. That means it is the ratio of B upon H, but in a particular medium other than air or vacuum. That means the magnet is placed in a particular medium other than air or vacuum. Then when the magnetic flux density of that magnet and magnetic field strength is calculated, and the ratio of these two is nothing but absolute permeability when it is measured in when the magnet is placed in particular medium other than air or vacuum is known as absolute permeability. Okay, suppose same ratio B upon H when measured in air or vacuum. The same ratio B upon H when measured when the magnet placed in a vacuum or air, then that ratio is known as mu naught. Mu naught is the permeability of free space or vacuum. When it is not placed in free space or vacuum or air, then it is called as absolute permeability, and when it is placed in vacuum or air or free space, then it is known as permeability of free space or vacuum. This mu naught is always constant and it has value of 4 pi into 10 raised to minus 7 Henry per meter, and it is always constant everywhere. Okay, this is the difference between this absolute permeability and permeability of free space or vacuum. Then another type we have, that relative permeability. The word relative suggests that there is a comparison between the quantities, so the word relative come here. The relative permeability, which is denoted by mu r, is the ratio of magnetic flux density in a particular medium, which is denoted by B, divided by magnetic flux density in air or vacuum, which is denoted by B naught. But the condition is that this B and B naught should be produced by the same magnet. That means the relative permeability mu r is the ratio of B upon B naught with same value of magnetic field strength H. Okay, B is the magnetic flux density in a particular medium and B naught is the magnetic flux density in air or vacuum or free space, which is denoted by this naught or this 0 at suffix. Okay, these are the different permeabilities. Then now, what is the relation between this mu naught and mu r, where mu is the absolute permeability, mu naught is the permeability of free space or vacuum, and mu r is called as relative permeability. Let's derive it. We have this equation B is equal to mu h for in case of a magnet when it is placed in a particular medium other than air or vacuum, and we have this equation B naught equals to mu naught into h when the magnet is placed in free space or air. Let's divide this equation by this equation. We will get B upon B naught is equal to this mu h divided by mu naught h. This mu h divided by mu naught h. So h is the same as we have seen here. H is the same, so h can be cancelled. We get the value of B upon B naught equals to mu upon mu naught, and we know that B upon B naught is nothing but relative permeability, so mu upon mu naught will be equals to mu r. So what is the relation between this mu naught and mu r? This is the relation. This equation shows the relation between mu naught and mu r, where mu is equal to the product of mu naught into mu r. That means absolute permeability is the product of permeability of free space into relative permeability of a material. This is the relation between these three parameters. Now we will see another parameter which is called as magnetomotive force, MMF. MMF stands for magnetomotive force, and MMF is the force responsible for the flow of flux or the generation of flux. It is similar to the EMF in case of electric circuit. We have already learned that EMF, that is electromotive force, is the force responsible for the flow of current in case of electrical circuit. Similarly, we have this force MMF in the magnetic circuits, which is responsible for the flow of flux. And this MMF is denoted by F and measured in ampere turns. We have this expression for MMF, which is denoted by F is equal to number of turns into current. So unit will be ampere turns. Then we have this another parameter, reluctance, which is the opposition to the flow of flux in a material, and it is denoted by S and measured in ampere turns per Weber. As in case of electrical circuit, we have resistance, which is the opposition, which oppose the flow of current in a material. Similarly, we have reluctance here, which opposes the flow of flux in a material. It is denoted by S and measured in ampere turns per Weber. We have this expression for reluctance, which is the ratio of MMF upon flux, and MMF is nothing but a number of turns into current divided by phi, which is measured in ampere turn per Weber. Now, let's see the analogy between electrical and magnetic circuit. This is the electrical circuit having this cell or battery having EMF, electromotive force, denoted by E. The R is the resistance of this wire connecting this battery, and I is the current flowing through this wire. According to Ohm's law, we can write that R is equal to E upon I, where R is the resistance of wire, E is the EMF, and I is the current. Okay. Similarly, we have this magnetic circuit where this is the iron piece, which is called as core, and on that core the winding is wound with n number of turns, and AC supply is given to that winding. When AC supply is given, the current flows through this winding, and which produces the magnetic field, and that causes the flux set up in this core. So the magnetic circuit is very similar to the electrical circuit. Here reluctance is the opposition to the flow of flux. Here resistance is the opposition to the flow of electrons or flow of current. Here reluctance is the opposition to the flow of flux. Here MMF is the force responsible for flow of flux. Here EMF is the force responsible for the flow of current. And so we have a similar relation between the Rm, MMF and phi, as Rm equals to MMF upon phi, where Rm is the reluctance of core. This is the similarities or analogy between the electrical and magnetic circuit. Then we have another parameter which is called as permeance. It is the reciprocal of reluctance, and it is the property of material to allow the flux to pass through it. Okay, so permeance will be 1 upon reluctance, and which is measured in Weber per ampere turn. These are the basic concepts related to magnetic circuit. Let's solve one numerical based on that. The question is, an iron ring of mean circumference 0.8 meter is uniformly wound with 500 turns of wire. Calculate the value of flux density that a current of 1.1 ampere would produce in the ring. Assume mu r is equal to 1400. Let's write plus given data. L is given, that is mean circumference of iron ring, which is drawn here. This is the iron ring having mean circumference 0.8 meter, and we have this n is equal to 500 number of turns wound here, and current is 1.1 ampere. Here we have written the given data, and we have to find here B, that is magnetic flux density for this given data. So let's solve this. We have the relation between B and H. B is equal to mu H. If we can find this mu and H, then with the help of this mu and H we can find this required value of magnetic flux density. So let's calculate that. First we will calculate the magnetic field strength H. We have this expression H is equal to N into I upon L. So putting the values of N, I, L, 500 into 1.1 divided by 0.8, which is equal to 687.5 ampere turns per meter. And we have mu is equal to mu naught into mu r. Mu naught is 4 pi into 10 raised to minus 7 into 1400. We will get this value. Then putting these two values in this equation, B is equal to this value of mu into H, we will get 1.209 Tesla. This is the value of magnetic flux density, required magnetic flux density for the given data. Okay, this is all about the various basic concepts related to magnetic circuit. In the next session, we are going to discuss Faraday's laws of electromagnetic induction. Till then, stay tuned and keep learning. Thank you.